All right. Welcome back to chemistry class. Those of you who are still awake. Today we're going to talk about heat capacity.
Wow.
Wow.
Excited.
What is that? Well, capacity is like what you can store, and so heat capacity then is how much heat an object can store. Typically we think of storage of heat captured in water typically, and there's a reason why. And so there's actually two factors that affect how much heat can be stored in something. First is the mass of the substance. How much stuff do you have? The more mass you have, the more heat you can store. So if I wanted to store massive amounts of heat, I would need a lot of something to capture it. The second thing is what type of substance. Different things store different amounts of heat. And so water is a good storage device for heat because it has a large specific heat. Things like metals don't store heat very well. They just get hot. And so we want things that don't get very hot and take a lot of energy in order to change their temperature. And so we call that a high specific heat. Pause here. All right, let's move on. So what is this specific heat that I'm referring to? The specific heat is defined as the amount of heat required to raise 1 gram of a substance 1 degree Celsius. This sounds like some other definition from our opener today. What does it sound like?
Calories.
It sounds just like calorie. But there's one tiny difference in this definition, and the word here is substance. In calorie, it's not substance, it's actually water. It turns out the specific heat has the same definition as a calorie. The only difference is that a calorie is the specific heat for water. Everything else that's not water has a different specific heat, specific to that substance, hence specific heat. The symbol here is C, capital C. I'm actually not sure why. There's actually two different types of specific heats. One's called CP, one's called CV. One was calculated at constant pressure, and what's calculated at constant volume. They're slightly different. In this class, we're going to assume that they're the same thing, and so we're just going to treat them all as a specific heat. Okay. So, take a look at this table here. This table here has lots of information, and all the numbers are different. Well, why are they different? Because they are specific to the substance. What is the highest specific heat on this chart? Liquid water. Very good. And what does it tell me the specific heat is? 4.184. That number looks familiar.
That's true.
Hey, that's the number of joules in 1 calorie. Turns out the specific heat of water is 1 calorie.
Whoa.
Wow. Wow. Okay. So, calorie is the specific heat of water. You're back. Let's move on. The higher the specific heat, the higher the amount of energy it takes to change the temperature. This always reminds me of when I go to the grocery store and I want to buy something from the produce department. And when I was a kid, I didn't realize what their prices meant. And it would say things like 99 cents /LB. And in my head, I'm thinking, oh, it costs 99 cents. And when I go to check out, they'll say, hey, this thing costs $3, and I'm confused. What I didn't understand was that sign /LB means per pound. It's 99 cents for every pound, and so they'll actually weigh it when you check out, and they'll charge you 99 cents times the number of pounds of whatever you bought. Do you understand what I'm talking about?
Yes.
This is especially true when you go to the mall and there's this thing called the sweet factory, right? And it'll say things like, everything costs, I don't know, $8.99 a pound. And you go and you just get different types of candies, right? And then they weigh it, and they multiply it by the cost per pound. You walk out and you just spent $20 on a bag of candy.
Basically.
All right, so what kind of units does these specific heats have? Oops, I'm still in highlighter mode. What kind of units?
Joules.
It's actually joules per gram
At Celsius.
degree Celsius. The other possible one is you can also have a specific heat in calories. Why do these units look like this? Well, do you remember when we talked about buying things per pound? It would be like /LB. This is joules per gram, but also per degree Celsius. Which means that if you're trying to heat 2 grams of water, then it would cost twice as much, about 8 joules. Or if I wanted to heat up 1 gram of water, but 2 degrees, it would also cost me twice as much, also 8 joules. And so instead of multiplying by the number of pounds, we're actually multiplying by the number of grams and the number of degrees, and that is my total cost, or the total amount of heat that's necessary. Questions about this? Okay, then what's low specific heat on this chart then? Gold and lead and silver and this thing called iron. So when it's really hot, like during the summer, you get in the car, there's a few things that are like extra, super high temperature. The steering wheel and the seatbelt buckle.
I branded myself once.
That buckle is extra hot because it has a low specific heat or low cost. It doesn't require a lot of energy to increase the temperature of iron because it has a low specific heat, and that's why the temperature of that buckle is much higher than the other things in the car because of this low specific heat. If we made that seatbelt buckle out of, say, lead or gold, it would be even hotter because it has an even lower specific heat. Making it out of aluminum should decrease the heat because aluminum has a specific heat of 0.9 instead of 0.4. So the equation I have here is Q equals M times C times delta T. We use these for what we call no phase change calculations, meaning that they don't change from solid to liquid or liquid to gas. They stay in their state of matter. So it's liquid to liquid or gas to gas. The only thing that changes is generally the temperature. Let's walk through all of these letters. What do you think Q is? Heat. It doesn't have to be in calories. It can also have units of joules. So Q can be in joules or calories. We spent time converting between them on our opener today. What is this M typically used for? Mass. We talked about how heat capacity is affected by mass, or the amount of something. And what do you think this capital C stands for? No. Capital C stands for? No.
Celsius.
No. It stands for specific heat.
How do they use
I don't know why they used specific heat as capital C, but we just wrote this on the last slide.
You're right.
Delta T is change in temperature. This is what I typically call T final minus T initial, or T2 minus T1. It's basically, is the temperature increasing or decreasing? If it's increasing, it's generally positive. If it's decreasing, it's generally negative. The formula for this is T2 minus T1. It'll give you generally whether it's increasing or decreasing. All right, so let's do an example now. So the first thing I want you to do when you look at this example is to circle or underline or mark the given things. There's lots of things that are givens. These are called, I refer to them as givens. Okay? Basically, mark or identify the givens. Now, I don't want you just to mark them. I actually want you to actually label them. So I call this marking and labeling your givens. When I say label them, I mean put a letter next to it that matches. So if I circle 5.0 grams, I would actually put an M here that represents mass. Are we okay with this?
Yeah.
Do you think you can mark up the other givens?
Yeah.
Okay. What is the equation we want to plug this into?
Q
Equals. Okay. Let's plug things in. So we don't have Q. Do we have M?
Yes.
Yes. 5.0 grams.
Plus.
Do we have C? What is that? Ah, there's one more thing.
Water.
Oh. Because it tells us the substance, we can then look up the specific heat of water. But we already know the specific heat of water. It is 4.184, because that's what 1 calorie is equal to. Now, these units for specific heat are weird. Again, it's joules over grams degrees Celsius. And then we're going to input the delta T at the very end. The delta T is the difference between T2 and T1. Something like that. So far, so good? All right. We cancel my units. Grams, grams, degrees Celsius. Fully canceled out. My answer then should be in joules, and all I have to do is multiply these three numbers together. Go ahead and do that. I'm going to check in with you. The correct answer here is negative 420 joules.
Why 420?
So, first of all, did you count sig figs?
Yes.
Okay, then I expect your answer to have 2 sig figs, hence 420.
Oh, you're right.
Is your answer negative?
Yes.
Excellent. And do you have a joules at the end?
Yes.
Beautiful. I want you to think of this Q as kind of like a delta H. When delta H is negative, that implies that the reaction is exothermic. A negative Q is a lot like an exothermic reaction. It means that the heat is being lost. How do we know the heat's being lost? Well, I'm starting at 35 degrees Celsius and I'm ending up at 15 degrees Celsius. This implies that heat has went away from the water, or the water lost heat to something else. Cool? What do you think a positive Q would represent then?
Endothermic.
Which means that it would then be absorbing heat and getting hotter. Shall we try another example? Let's try a new example. All right, let's move on. Okay. Okay, so I just talked about how when Q is positive, it's endothermic, Q is negative, it's exothermic. It's a lot like delta H. You can think of Q and delta H as essentially the same kind of thing. No, I mean, they're essentially the same thing, right? Cool? If you need to, you can always refer back to the video later. I'm moving on in the interest of time. Here's your second example. If the temperature of 30 grams of ethanol increases from 25 to 75, what is the change in heat energy? Okay, let's plug in some values here. We don't have a Q. Do we have an M?
Yes. M is 30.
30 grams. The specific heat here, we're going to use ethanol, which is 2.44 joules per grams degrees Celsius. And we're going to have a delta T, in this case of 75 minus 25. Again, the units are going to cancel nicely, and we should end up with 3,700 joules. This time it's positive, which implies that the heat is entering or being absorbed by this specific liquid. T2 minus T1.
Is final minus initial.
Final minus initial. Then you can tell whether it's increasing or decreasing. Another way of thinking about it is if you find the difference, then you can assign a sign whether it's going up or down, whether it's positive or negative. The difference is clearly 50, and it's going up, so it should be a positive 50. And you get a positive 50 by subtracting 75 by 25. Okay, let's do another one. We're going to make time for another one. Skip all of this wonderful stuff. Oh, what happened to my example 3? Oh, there it is. Okay. I want to make sure to slide this one into our notes because this one actually looks a little bit different than the one before. And so we actually have to set this one slightly differently. I'm going to assist you by circling a few things for you. This one, this thing here, this one here, and also this one down in here. I'd like you to identify what those things are, and then we can plug it into the equation. So you're going to be solving for the specific heat, and you'll find the specific heat is 0.90 joules per gram degree Celsius, which then leads you to the fact that it's aluminum. Alright, so let's plug in some values. We have a Q value of 453 joules. We're going to set this equal to 5.0 grams. Our specific heat is unknown, but we do have a delta T. Our delta T here is going to be 122 minus 21 degrees Celsius. And to solve for C, we're going to divide both sides by 5 grams. We're also going to divide it by 101 degrees Celsius, the result of that subtraction. We can see that the units don't cancel here, and so C is going to end up being 0.90 joules over grams degrees Celsius, which is the unit for specific heat, and this is how we get an answer that is closest to aluminum. Alright, so here we have example 4, and in this case we're told that this item is granite, and it also that it loses 240 joules of heat. If we set up into our equation here, we can plug in a Q of negative 240 joules. And the reason we know it's negative is because of this word loses, which implies that it is a decrease or a loss of 240 joules. Our mass is still going to be 12 grams. Our specific heat is going to be coming from this chart here, and we're looking specifically for granite. So it's 0.803 joules per gram degree Celsius. And the delta T here, I'm going to go ahead and leave as a variable. So, there's a couple of things we can do to cancel our units. Go ahead and do that now. Joules can be canceled on both sides, as well as grams, which should leave degrees Celsius as my final unit. So to solve for delta T, we're going to go ahead and isolate the variable here, and we're going to divide both sides by 12, and we'll also divide both sides by 0.803. And the units technically are 1 over degrees Celsius. When you do this division, the degrees Celsius will pop back on top, and you'll get a delta T that's actually in degrees Celsius. So delta T here is going to be 25 degrees Celsius, which implies that we've actually, the temperature should have gone down by 25 degrees Celsius. The question is asking us to find final temperature, and so we can set this negative 25 degrees Celsius as equal to T2 minus T1. And so when we plug in our 22 degrees Celsius as my T1, then I can solve for T2. T2 in this case is going to be negative 3 degrees Celsius.